So good evening to all of you. This will be the 5th lecture in the series of chemical measure trace and ultra trace analysis. And in this lecture, we'll be looking into this part, the mass spectrometry and hyphenated techniques, application classification needs, and this part it will be seen throughout this lecture. So hyphenated techniques, the basic principle, instrumentation, its application, classification, need for hyphenation, and in various interfacing devices and their applications like GCMS, GCIR, LCMS. Few of all, not all can be covered in this period of time. So only we'll look into the major instruments like GCMS, LCMS, and few. And so now, what is actually a hyphenated technique? We know that any analytical technique has some stimulus has to be given to the sample. Stimulus can be in the form of light, heat, current, or voltage. Then something will happen, like the sample will interact with this stimulus. Then the detector will measure the interaction, and then your signal will be processed, and some readout will be coming out, from which we can calculate the concentration of the analyte. So now a hyphenated technique in analytical chemistry actually refers to the combination of 2 or more analytical methods to enhance the separation, identification, and quantification of chemical compounds. It typically involves coupling of a separation technique, for example, chromatography, with a detection method, for example, mass spectrometry or spectroscopy. So this is called hyphenation. So this scientist in 1980 introduced the term hyphenation, which is of a separation technique and 1 or more spectroscopic detection technique. So now the number of existing techniques has been combined to expand the utility. So based on the utility, based on the requirement, the various techniques are combined, and then people can do more and more research. Now the direct conjugation of chromatographic technique with spectroscopy examination of separated fraction constituent several powerful analytical techniques. So now, sometimes a slash is given in terms of a hyphen if one of the technique is already containing a hyphen, like HPLC slash ESI-MS. ESI is nothing but electron spray ionization mass spectrometer. So these are the terminologies. So recently, more than 2 techniques coupled together to form a more powerful integrated systems have revolutionized and the trace element analysis industry. So, like you can see, liquid chromatography, PDA, and mass spectrometry. Now this is polychromator diode array. So that is liquid chromatography, and then diode array, and then mass spectrometer like LC-MS-MS, LC-NMR-MS. Instruments have become available and have been applied to pharmaceutical problem solving, many other things. So this is solid phase extraction, liquid chromatography, MS. So like this. Now the combination can be separation, identification, and identification techniques. So like solid phase, like this one, solid phase extraction or large volume injection or thermal lens spectrometry can be coupled to separation technique like GC, HPLC, or capillary electrophoresis. Then this is hyphenation, and then the detection technique also can be different, like PDA, poly diode array, or IR, or mass spectrometer, or NMR, or now this thermal lens spectrometry. For the detection techniques also can be happened. Again, the MS can come, and so it will be MS-MS. If one more MS here come, then it will be MS-MS. So that is tandem techniques. So These are the terminologies. Now, what are the advantages of these hyphenation techniques? So to list out, you can have enhanced selectivity, like for example, GCMS separates and identifies various volatile organic compounds. You can have improved sensitivity, like it detects trace level components due to highly sensitive detectors. For example, LCMS identifies drug metabolites at parts per billion level. You must be aware of ppb and ppm, which were the various concentration units for your analyte concentration and covered widely in your first lecture. Then accurate identification. So this provides precise molecular identification through structural analysis. Now, like example is LC-NMR, which identifies unknown organic compounds by chemical structure. Simultaneous analysis. So it performs separation and detection in a single run. So it saves your time. So you don't have to first separate and then to do. If you are using some separation technique first, then you have to separate it, then you have to analyze by the instrument. But instead, if you are using a hyphenation technique, then the components will be separated and identification or quantification will be done at a single shot. So that will save your time. Now, high throughput, because it saves the time, so you will have high sample throughput. Now, minimal sample preparation, also you don't have to physically use any separation technique. Already instruments are there who can separate for you, and then you can combine it with the detection technique, and therefore minimal sample preparation. And versatility. So applicable across various industries, including pharmaceutical, forensic, and environmental monitoring. For example, GCMS is widely used in drug testing and toxicology, and like that. So now to list a few hyphenated technique, I have given the list here. So in between this, we have already seen ICP-OES in our last class. Like then in this class, we'll be covering ICP-MS, GCMS, LCMS to a great extent, and all other things that we'll touch upon. And so what is ICP-MS? Let us first look into ICP-MS. So what is ICP-MS? As the name is suggesting, your inductively coupled plasma or ICP is combined to a mass spectrometry, which is MS. So ICP-MS. So mass spectrometry method, normally what it does, it detects ions distinguished by their mass to charge ratio and by Z value. So based on ions moving under influence of electrical or magnetic field, they can be separated. So mass analyzers are used to separate these masses based on their mass to charge ratio, and they normally require operation under vacuum to avoid ions colliding with other particles. So now the block diagram of one ICP-MS, typical ICP-MS instrument is shown here. So now you can see your ICP-MS will have a sample introduction. So this is a sample introduction up to this. But it is totally a sample introduction technique. This one. Then your sample ionization is the plasma. So sample ionization part. Then now your plasma is in atmospheric pressure. So from this, the ion needs to be taken into the mass spectrometer, which is under high vacuum. So there must be an interface. So this is a plasma vacuum interface. Then now their ion optics will be there who can guide your sample to the mass spectrometer. And finally, this is the mass separation device, and then this is the detector. So these are the various parts of a mass ICP-MS, which has been, the block diagram is shown here. Let us see one by one part elaborately. So now, what is the sample introduction system and its component are given here. So this is a real picture of one system. So you can see this is the total sample introduction system, which is this is a peristaltic pump, this one, and this is the nebulizer, this one, and this is a spray chamber. So now let us see what they are used for. So now the sample introduction system is utilized to convert the liquid sample into an aerosol, and then they are transport the small droplets of around 5 to 10 micrometer in diameter size will be transport to the plasma, the inductively coupled plasma, and the large droplets will be discarded as if they will pass to the plasma, then plasma impedance will change and then plasma will shut down. So therefore, they are not normally sent to the plasma. So now the different part of this nebulizer is a peristaltic pump, which are typically used to control the sample intake rate, because the sample intake rate should be similar for all the standards and samples, and therefore you use peristaltic pump. Now nebulizer, it needs to produce a fine mist for efficient sample introduction. So usually made up of quartz or PFA material, that is perfluoroalkoxyalkane material, or fluoropolymer, or and then a spray chamber. We need to discard the large particle size sample to save the plasma, and therefore a spray chamber will do that work to discard the heavy droplets. So now the sample introduction system, if you are taking a solid sample directly, actually solid sample can also be analyzed directly in ICP-MS, but for that you need a separate type of sample introduction system. As in my previous class, I have already told you that either laser ablation or graphite furnace or hydrate generation can be used as a solid sampling sample technique. So here I have seen the picture of a laser ablation. The laser ablation is a very powerful sampling technique for solid sample. Solid samples can be analyzed directly. Application including like geological samples or any sample which are very difficult for dissolution, some refractory materials can be done by this technique. So these techniques can have limited detection in the order of ppm, that is very good spatial resolution also you can get. So a powerful laser is focused onto the sample in an argon atmosphere or in some inert atmosphere like helium, so that the sample, whatever vaporized, it will not react with the environment. So now a tiny percent of the solid sample is vaporized, and the resulting sample containing aerosol is swept into the ICP, where it is atomized and ionized, and finally the ions are analyzed by the mass spectrometer. So the laser can be focused on different area of the sample and thus used for a spatial characterization of heterogeneous solid sample. Like it is called as mapping, like your solid is there. So now your laser can be put here, then slowly here, then here, like that you can map the total surface by focusing the laser at the various places. So this is a typical picture of a laser ablation system, where now there is a UV laser which is interacting with your sample, some vapor is being generated, and those vapors are now passed into your plasma. So this is what a laser ablation system is. So normally, but doing solid samples are really challenging because calibration is difficult. Normally you have to matrix match standards you need to have, because when you are using a soil sample, you don't know perfectly what is the matrix. So it is very difficult to calibrate your instrument when you are doing a solid sample. Quantitative analysis is also challenging because the laser can cause elemental fractionation, because once you are the material is getting ablated and few vapors are generated from the sample, but then the vapor may not be exact replica of your sample, or it is not homogeneous as your sample is. So that time fractionation will happen and it will be difficult to know the exact concentration. So due to ablation process, it is also said to be dependent on wavelength and pulse duration. So these effects can be overcome by using very short laser pulses, that is of the order of say femtoseconds or shutter wavelengths. Now the technique, although destructive, can be described as minimal invasive because of small size of sample crater, sometimes less than 100 micrometer diameter. So this is shown, which is formed by some laser ablation technique, a small crater in your sample. So now aerosol is generated by the, also for solution sample, the aerosol is generated by the pneumatic action of gas flow. So like 1 liter per minute, smashing the liquid into tiny droplets. So these are two types of nebulizers shown here. One is concentric nebulizer and another one is cross flow nebulizer. The concentric nebulizer is for very clean samples where your salt content is very less, like less than mostly 1000 ppm, your total salt content. But in case this cross flow nebulizer can be used for heavier metrics, and even small amount of undissolved materials if present, then also it can be used. So it is more rugged one. Now, the organic solvents, sometimes like ultrasonic nebulizers are there. So like organic solvents, if introduced into ICP-MS, can be destabilize the plasma. Carbon can also act as an interferent, and that time you can have some ultrasonic nebulizer, which will form some vibration by ultrasound. Vibration will be created where your solvent will be evaporated, and then the solvent-less sample can be sent to the plasma. So this is the ultrasonic nebulizer. Now the most common one and most like the workhorse you can tell of analytical chemistry is the ICP source or inductively coupled plasma source. So this we have covered in our last class also, but just more elaborately I want to cover it here. So now the plasma, this is a typical picture of a plasma. This is your plasma torch actually, which is made up of quartz. From this to this, it's a plasma torch made up of quartz, of which you can see there are 3 concentric glass tubes. This is one, this is second, and this is the third glass tube. So these are the 3 glass tube in the plasma torch. So now your cool gas, argon, normally most of the plasma are formed by argon plasma or argon plasma. So now your argon gas will be flowing through this at a very heavy rate of 12 to 70 liters per minute. And then through this as auxiliary flow of 0 to 1 liter per minute. And then through this is the sample or nebulizer gas. Again, 1 liter per minute is the flow rate. So now this gas flow, this sustains the plasma. So the flowing gas is seeded with electron. How the plasma is formed is that now once your gases are flowing through this, now the argon gas is seeded by some electrons by a high voltage spark using a Tesla coil. Now these electrons undergo acceleration by the rapidly changing electromagnetic field, because now you can see these are the RF induction coils through which your RF power will be passed. So now this is the so this RF power, now you know that whenever there is a alternating current passing through a coil, so it will generate a magnetic field. So there is an electromagnetic field will be forming. Now the seeded electron will be undergoing acceleration by the rapidly changing electromagnetic field, and gain the energy necessary to excite and ionize the gaseous atoms by collision. Now this produces the plasma, which is a self-sustaining. As long as you are passing the RF current here, the electromagnetic field is there, there is acceleration of the electron is there, and therefore your plasma will be sustained. Once you stop the RF power, so your plasma will shut down. So this plasma has a multiple temperature zone, as has been shown here. You can see 6,000, 8,000, 10,000. So maximum temperature of the plasma is 10,000 degree Kelvin, but the analytical zone has a temperature of around 6,000 to 6,500 degree Kelvin. So now how the ions are forming here. So now you can see the various zones are shown here, analytical zone. Now when your aerosol is passing through this, now once it reaches here where it is the very high temperature, the solvent will lose, so solid particle will be forming, then solid will convert it to gas, then atoms, then to ions in analytical zone. So this is the process through which your sample in the, like your analyte in the sample will be getting atomized and ionized. So the sample undergo number of physical changes starting at the preheating zone and then continuing through the radiation zone before it eventually becomes a positive charge ion in the analytical zone. And mostly singly charged positive ions are generated in this case, which has been now entering into the mass spectrometer, and there they will be separated as their mass to charge ratio. So now this is the interface zone which has been shown here. You can see this is the interface. Now this is your plasma and this is the RF coil. You can see this is the RF coil, this is the plasma, and this is overlapping on the interface zone. So interface transport the ions efficiently and consistently from the plasma source, which is actually the plasma source is your at atmospheric pressure, that is 760 millimeter of mercury or 760 torr, from which now on inside it is very high vacuum. The interface zone it is 1 to 2 torr, and during the in the mass analyzer zone it is 10 to the minus 6 torr. So you can see it is a very like gradation of pressure is there. So there is a need of interface from where the ions will be entering to the mass spectrometer zone. So that is, there are two cones actually. One is sampling cone and one is skimmer cone. So these two cones, sampling cone is having 1 millimeter of orifice. So all the ion cloud forming in here in the plasma, they will be entering into the sampling cone, and then from there to the skimmer cone, and then finally it will go to the your mass spectrometer. So now once the ions are forming and it is entering into your mass spectrometer, where your skimmer cone is, sampling cone is there first, then your skimmer cone is there, and then because it will whatever ion cloud has entered inside, it will consist of normal particulate matter also, then negatively charged ion, electron, and many other unionized product also. So these are not needed in mass spectrometer. We are only interested in the positive ions, which are finally now. So there will be a need of ion optics. The role of the ion focusing system is to transport the maximum number of analyte ion from the interface region to the mass analyzer, and also to reject the photons, neutral components, and other matrix components. So now the ion extraction lenses in ICP-MS perform an essential function of separating the ions from the photons and the residual neutral material for the lowest background signal and highest sensitivity with efficient interference removal. So now you can see this is the plasma touch. Here plasma will be there. Now here it is the sampling cone, skimmer cone, and here this the ion optics is here actually. Ion lenses, you can see it is shown here. This is the ion lenses. Then there is a collision reaction cell, and then finally the quadrupole mass analyzer. So what is this? So we'll just see. So now there are various types of mass analyzer. Mass analyzer is nothing but like in case of your normal spectrophotometer or atomic absorption spectrometer, you have seen monochromator is used to separate the various wavelengths. Like that, in case of mass spectrometer, your mass analyzer is used to separate the various mass ions based on their mass to charge ratio. As you know, that when the ion cloud itself is entering into the mass spectrometer, if the ions all together they will reach to the detector, then it cannot count or cannot identify or quantify individual ions based on their M by Z ratio. Therefore, it is very much needed that the ion cloud, the ions should be separated from the total cloud depending on their mass to charge ratio. So there are many types of mass analyzer are there. The most common mass analyzer are these three. One is quadrupole, which is widely used due to its ease of use, robustness, mass range, high scanning speed, and resolving power. About 300 at 300 AMU is the resolving power. So it is relatively low cost. So normally, what do you mean by 300 at 300 AMU? AMU, that you know that resolving power R is equal to actually M by delta M. So resolving is 300 at 300 AMU. That means this is 1. So your quadrupole mass spectrometer in general can resolve your 1 AMU mass difference. Like you can count, you can see 210 and 211 masses, but not if there is a mass number at 210.5, then it cannot be resolved from 200. So therefore, this is a 1 AMU mass resolution. There is the magnetic sector, which is a very high resolution mass spectrometer, and here there is an electrostatic field, and then there is a magnetic sector. So by this combination of these two, your masses will be separated. Now there is one more thing, is the time of flight, where your masses, all the bunch of masses will have different mobility based on their masses. So heavier mass will move slowly, and then lighter mass, because their kinetic energy being same, your heavier ion will move slowly, then lighter ion. So lighter ion will fall on the detector first. So they are depending on this principle, the ions will be separated in time of flight mass spectrometer. So an ICP quadrupole with collision cell reaction. So to overcome polyatomic interferences, collision reaction with or collision cell or reaction cell with the gases such as hydrogen, helium, ammonia is placed before the mass analyzer, which consists of a multipole, that is quadrupole, hexapole, octapole, usually operates in the RF only mode. You have seen that quadrupole actually operates both in RF and DC mode, but here the reaction cell operates only RF only mode. So collagenal induced dissociation reaction on polyatomic ions such as oxygen plus, then ArCl plus, ClO plus separates the ions analyzed from iron, arsenic, and vanadium, etc. So interferences will be removed. So alternative methods such as high resolution ICP-MS, multi-collector inductively coupled plasma mass spectrometer are also used for removal of polyatomic interferences. So now, just to stress upon what I mean to say is here I have given a table. You can show this is the isotope, this is the matrix in which they are being analyzed, and what is the interference causing element. So for a typical case, you can say the calcium. Now calcium also, you know, the mass is 40. Argon also the mass is 40. So if you see, then for in case of normal quadrupole mass spectrometer without any reaction cell, like here anyway both are elements, so reaction cell or collagen cell also will not work for with the resolution of 1 AMU. In case of normal ICP-MS with quadrupole mass analyzer, it will look like this. So both will come at the same place. Now here it is seen as iron 56 and argon oxide 56. The case it's shown here is this one, iron 56 and argon oxide 56. So now you can see argon 40 and oxygen 16, total 56, and iron also is 56. So this both ion with this plus ion, it will come at the same place. And here also in case of calcium and argon, they will come at the same place. So now how to separate them? So to separate them, you see the resolving power is given here. So what does it mean? Say this case, we will see. This is the required resolving power is 199800. What does it mean? So you can see here, I have explained it, calcium 40. Exact mass actually if you see, then it is 39.962591. Like that, argon 40 exact mass is 39.962383 mu. So what is the difference in mass is only 0.00208 mu. So if you want to have two different peaks for these ions, then you require a resolving power of around this. So because as you know, resolving power is nothing but m by delta m. So now delta m is this, m is 40. So resolving power required is this much. So therefore it is written here. So this much resolution is required for your mass spectrometer, and that is possible only in case of magnetic sector mass spectrometer. For quadrupole, it will not be possible anytime. So now let us see the various type of detectors. Now there are various type of detectors. One is Faraday curve. It is high accuracy and long-term stability suitable for precision isotope ratio measurement, and its sensitivity is limited by the capability of the electronics. So now how is your electronics? Depending on that, the Faraday curve collector, and it is used for when your concentration is very like in higher side. And second one is the electron multiplier. So they have sufficient gain to detect very small current with high signal to noise ratio and good linearity. So when you are working in PPT or sub PPB range, like PPT or sub PPB range, then you can use this electron multiplier. But when in ppm range, if you are working, then you can use your Faraday curve also. So electron multipliers are perhaps the most common detector in modern mass spectrometer due to their exceptionally high gain and low noise. A single ion entering the front of the multiplier can result in upward of around 1 million electrons existing in the bed. So this type of 1 million times your signal can be improved. Now there is advantages and disadvantages of ICP-MS, because any element you see, there are always some advantages are there and also some disadvantages are there. So for ICP-MS, though it is a very good technique and workhorse for an analytical lab, it has various disadvantages also. So let us look into its strength and weaknesses. So it is wide elemental coverage, as you can see in this periodic table given here with all this color code, whatever that means. You detect the color code represents the detection limit. Like green color detection limit is 10 ppq. Means ppq means it is less than ppt. Okay, so -9 is ppb, -15 is ppt, and so on. So that is you can have it is detection limit. Then for blue color, it is less than 100 ppq. Yellow color, it is less than 1 ppt. Red, it is 10 ppt. And the pink color or magenta color, it is 50 ppt. So you can see, have a look to this, the detection limiter given here. So the performance-wise is a high sensitivity and low background signal combined to give very low detection limit, sub-nanogram per liter or parts per trillion or parts per quadrillion also. The fast analysis time with a high-speed scanning quadrupole analyzer, wide dynamic range up to 9 error in a single acquisition. So isotopic information is possible, which was not there in case of your spectrometric techniques, where you are using photon as your signal. So there it is very difficult to use your isotopic information, but here you can get the isotopic information because the ions are separated here based on their mass to charge ratio. Now it is spectral simplicity. What does that mean? Actually, you can look here. Here it is a spectra of around 10 ppm of cerium. So this is a ICP OES spectra. This is an ICP OES spectra. In comparison to the same solution, this is a ICP MS spectra. So you can compare what is the mean of the spectral simplicity. So in case of mass spectrometer, it is very simple spectra. Because mass spectrometer, like say for cerium, there are only two masses are there, 140 and 141. Two isotopes are there. So only 2 peaks for cerium. And these are all for other interference like argon, hydrogen, argon, oxygen, and all other things. But for the same cerium, you can have multiple emission lines. So therefore, the spectral simplicity is there in case of mass spectrometer. Now, what is the disadvantage? It is prone to mass interferences, low tolerance for TDS, usually less than 0.5%, difficulty to analyze complicated matrices, more maintenance, and associated cost. Actually, it is the capital cost as well as running cost is very high for ICP-MS. So now, what are the applications actually? So determination of isotopic ratio of boron in gadolinium. It is a very versatile technique which can be used for analysis of this type of all the types of materials, starting from nuclear materials, clinical and pharmaceuticals, geological, forensic, chemicals and pharmaceuticals, again then food and agriculture, like that. So now let us come to GCMS. So what is GCMS? It is nothing but gas chromatography mass spectrometry, and it is a method that combines the feature of gas chromatography and mass spectrometry to identify, quantify different substances within a test sample. So this is a sample, this is a gas chromatography, and this is a mass spectrometer. So now this is your sample. Now through the gas chromatography, all these sample components can be separated. Once separated, one by one, they will be passing to the mass spectrometer where they can be identified and quantified. So this is a gas chromatography mass spectrometer. The sample is vaporized, injected into a carrier gas, and passed through a capillary column with a stationary phase. The components separate based on the boiling points and interaction with the stationary phase. Now the components of the sample, they will be getting separated based on their boiling points and interaction with the stationary phase present in the column. Now the separated components then enter into the mass spectrometer where they are ionized and then fragmented and analyzed. Now fragments are separated by M by Z and detected, generated a unique mass spectrum for each compound. As you may be knowing that for each and every compound, there will be the mass spectrum will be unique. So based on that, you can identify that the compound, and taking any one ion, say maybe the molecular ion or the most abundant ion, you can quantify them. So now GC separates components, MS identifies and quantifies them based on their mass spectra by comparing data with a reference library. So all the instrument will be having a reference library. So from that, it will suggest you what can be the your compound is. So this general schematic of a GCMS, here it is the injector. So yes, you can inject your sample. So now this is a column where it will be passes, and then they will get separated. Then through that it will pass to the mass spectrometer. Now this is the ion source, either electron spray ionization source or chemical ionization source will be there. Then mass analyzer, then detector. So this normal commercial instruments looks like this. So now what are the applications? So now GCMS, it can be applied to environmental analysis. So now for each one example I have given, like environmental analysis, it can detect your pollutants, pesticides, volatile organic compounds. Then one example is monitoring air and water quality. As you all know, nowadays it is very much like important to monitor the air and water quality, because a lot of pollutions are there. So for all these things, GCMS is the best technique. Now, food and beverage industry, flavor and fragrance analysis, detection of food additives, contaminants, and spoilage indicators, like ensuring food safety by detecting pesticides residue in fruits. For pharmaceutical industry also, it is very widely used, like drug purity testing and stability studies are done. The identification of active pharmaceutical ingredients and impurities will be there. So analyzing drug formulations during quality control samples are there. Then forensic science, drug testing, toxicology, explosive and arson investigation. Now, for example, detecting illegal substance in forensic samples also is present. You may be knowing, like some times the athletes will be using some illegal substance to increase their efficiency. So all these things can be done here. Now, clinical diagnostic also, it is helpful. Identification of biomarkers and metabolites, like detecting your metabolic disorder through blood or urine analysis. All these things can be done by GCMS. Also in petrochemical industry, chemical and material research, biochemical research, cosmetic industry, or any regulatory compliance and quality assurance. So there are a wide variety of use of GCMS. You can use that. But for all the applications, the column, same column cannot be used for all the applications. There are various types of column, different columns. So once you are started using your GCMS, you can have an experience on what are the columns which will be applicable for what type of work. So columns may be different. Now, what are the advantages of GCMS? It is very highly sensitive and selective. Detects compounds at trace level, again ppb to ppt, because mass spectrometer is involved. So normally we can approach to ppb to ppt, or sometimes if you are telling in moles region, then nanomoles to picomole region also can be analyzed. So like pesticides in your food samples can be done very well. Accurate and qualitative and also quantitative. If you just want to know what are the various components present in the sample, which is called as qualitative, that, as well as if you want to quantify them, that also can be done here. So wide range of applications, as you are seeing, suitable for environment, pharmaceutical, forensic and clinical samples, automated and high throughput, reliable identification, and reproducibility and accuracy is very good. And actually one more important point is small sample size. So you can imagine only 1 microliter or 2 microliter of sample is required for analysis in GCMS, which can give you a very good signal. So very few sample size is required. But yes, there are some disadvantages also, like limited to volatile and thermally stable compounds, because it is a gas chromatography. So now your component which you are going to analyze should be a volatile one or not. If not volatile at room temperature, then it should be converted to vapors by applying some temperature. So around 300 degree is allowed in GC, and that in that 300 degree centigrade up to is allowed. So in that range, again, your sample should not get decomposed. So now it is limited to volatile and thermally stable compound. And obviously high capital cost, one GCMS may be crores of rupees, it is required. And complex method development, because you cannot inject your blood samples or serum samples or urine samples directly to GCMS. That will spoil your column. You need to separate your analyte into some organic solvent, and then the organic solvent can only be injected into your GCMS. So though it is a very versatile technique and it can address all type of matrices, but you require to develop a method for each and every matrix. Sample preparation requirement. It requires very extensive sample preparation. Like as I have told, you always have to extract your analyte into some organic solvent, and sometimes if the analyte is not volatile, then you have to derivatize it to make it volatile by doing some organic reaction, and then you can identify and quantify it. So metric interference also can be there. Complex sample matrices can cause interference and reduce accuracy. Consumables and maintenance cost, capital cost, as well as running cost is high, and potential for contamination. Sensitive components may accumulate contamination over time, affecting your results. So now your pesticide analysis, these are the like 4 pesticides you can have, aldrin, linden. So these are the various pesticides. These are being analyzed in your GCMS. So these are the real spectra, what I am seeing, showing you here. So you can see this is a 1 ppm spectra for these compounds. So get complete GC spectra. So now let us see the liquid chromatography mass spectrometer. This is the hyphenated technique of HPLC with mass spectrometer. So this is the commercial instrument of Bruker, you can see here. So now LCMS is an analytical technique that combines the physical separation capabilities of liquid chromatography or HPLC, this high performance liquid chromatography, with mass analysis capabilities of mass spectrometry. Now the coupled chromatography to mass spectrometry systems are popular in chemical analysis because the individual capabilities of each technique are enhanced synergistically. So while liquid chromatography separates the mixture with multiple components, mass spectrometry again provides structural identity. So what is the difference between GCMS and LCMS? This can handle liquid samples and GC can handle gaseous samples. So now this tandem technique can be used to analyze biochemical, organic and inorganic compounds. Again, it is a versatile use. So now the high performance liquid chromatography is a powerful analytical technique used. Now here, how they are, like there are 3 types of different types of chromatographic techniques are there. So now liquid HPLC, then size exclusion chromatography is there. Then reverse phase HPLC is there, most common, where the stationary phase is non-polar. Normally, this is 95% sample can be handled by this. So, and 95% cases are reverse phase HPLC, where it is a C18 column. And now, what is the mathematical actually expression is presented here. So now this is the TR, TM, and so this is the retention time of the analyte, and TM is the retention time of the unretained compound. So this is how it is done there. So this is a typical block diagram of your LCMS system. Now these are the various solvent or mobile phase kept here. So this the sample is your sample mixture are getting separated. So now LC to MS interface, the separated components are then passing to your mass spectrometer, finally detection, and then you can get a spectra. So in case of LCMS, primarily 2 types of ionization techniques are there. So one is electron spray ionization technique. So it is actually a soft ionization technique to produce ion from large, thermally unstable and non-volatile molecule. So the ionization process occurs under atmospheric pressure, making it ideal for biomolecules like proteins, peptides, and nucleic acids. So now the liquid sample from column is introduced through a capillary tube. A high voltage of 3 to 6 kilovolt is applied to the capillary tube, creating a solution like creating a strong electric field. Now the electric field causes the liquid to disperse into fine charged droplets due to electrostatic repulsion. Now these droplets have positive or negative charges depending on the applied voltage polarity. And as the charged droplets travel through a heated nitrogen gas stream, the solvent evaporates. Now droplets shrinks and increasing charge density, eventually leading to Coulombic explosion, where the droplet breaks due to electrostatic repulsion. And after multiple droplet explosion, isolated ions are released into the gas phase, and therefore there is a production of your cloud of ions, which can then be separated by their mass to charge ratio. So here it is given like high voltage is applied, sample through capillary is coming, so drying, and now it is getting exploded, and now it is the ions are passing to the mass spectrometer. So this is the second type of ionization is the atmospheric pressure chemical ionization, or APCI. It is a soft, and again it is also a soft ionization technique to analyze moderately polar and non-polar compounds. It operates at atmospheric pressure, and therefore the name atmospheric pressure. Ionizing analytes from a liquid phase introduced into the system as an aerosol. Now, APCI is commonly used for less polar, thermally stable compounds that are difficult to ionize by electron spray ionization. So the liquid samples usually dissolve in a volatile solvent like methanol or acetonitrile or water is introduced through a capillary into the nebulizer. Now a flow of nitrogen gas converts this liquid into a fine aerosol spray. Now the aerosolized droplets pass through a heated ceramic tube at around 200 to 500 degrees centigrade, where the solvent evaporates, leading to the analyte molecule in a gas phase. So our high voltage 3 to 5 kilovolt is applied to a corona discharge needle, creating a plasma of ionized gas molecule. Like so the plasma ionizes the solvent molecule, generating reactive ions like H3O plus, NO plus, and O2 plus. Now the analyte molecules react with these ions through proton transport, charge exchange, or adduct formation, producing the molecular ion. So you can see a typical example is shown here, the metal ion. Now like your molecule of interest interacting with H plus, and the charge transfer is happening, and then this ion is forming. Now the ionized analytes are directed into the mass spectrometer, where now they are separated based on their mass to charge ratio. So here a typical picture of this is given here. You can go through it. So I have given a comparison of these two ionization source here. So like sample type, APCI is for less polar, thermally stable. This is for highly polar and thermally labile. Ionization method, chemical ionization, electrostatic ionization. Here it is temperature around 200, 250 to 500. It's low to moderate. Now application, environmental, food and drug, this protein, peptides, and biomolecules. So this is a clear-cut comparison between APCI and ESI is given here. You can have a look. This typical mass LCMS mass spectrometer, where your samples are being separated. It is having, say, there are 4 components with 4 retention time, or T1, T2, T3, T4 are retention time. So these are the 4 spectra, and this is the mass to charge ratio, depending on that. So one example is given, like your aflatoxin are toxic metabolites produced by certain fungi in foods. Now figures show the total ion chromatograph for 4 aflatoxins. Each could be uniquely identified by the mass spectrometer. You can see now these 4 are there. So there is a 4 type of 4 peaks you are getting for all these 4 aflatoxin byproducts, metabolites. Now this tandem mass spectrometer is there. The tandem mass spectrometry, also known as MS/MS or MS square, is a technique in instrumental analysis where two or more mass analyzers are coupled together using an additional reaction step to increase their ability to analyze chemical samples. So a common use of tandem mass spectrometer is the analysis of biomolecules such as proteins and peptides. Now what it does is here, now there will be one mass spectrometer. So here these samples will be separated. Now again, if you have some doubts, so this will be again going into another mass spectrometer, and again they will fragmented there in the second mass spectrometer, and finally you can have a spectra related to that. Because it can so happen that during your first ionization, it can be contaminated with some ions which have same mass. But so you can confuse, like there can be an interference. Like in case of normal inorganic mass spectrometer, we have seen that there are isobaric interferences are there. So means two atoms having same mass, they can come at the same place of mass to charge ratio. Say argon and calcium, both are 40. They are coming at the same place. Similarly, in case of organic mass spectrometer also, when two molecules are having same mass, they can come at the same place at when you are doing a MS1 first mass spectrometer. But if now those masses or those ions are further being fragmented, then one molecule may get fragmentation pattern in a different way than your other molecule. So depending on that you can have an idea that, like see, now this is here, this is after MS1, you are getting a single peak for 3 different components. Now when they are getting further fragmented, you are having 3 different type of fragmentation pattern. So definitely they belong to, this is molecule 1, this is molecule 2, and this is molecule 3. So 1, 2, and 3. So we have different type of yeah. So these are the, therefore you can find out, like when you are doing MS/MS, or there are sometimes MS/MS/MS. So these are the benefits. So you can go through the literature, like the molecules of a given sample are ionized, and the first spectrometer designed as designated as MS1 separate these ions by their mass to charge ratio, often given as M by Z or M by Q. Now ions of a particular M by Z ratio coming from MS1 are selected and then made to split into smaller fragment ion by any of the following technique. Either you can use collision-induced dissociation, or ion molecule interaction, or photodissociation. Now these fragments are then introduced into the second mass spectrometer, which in turn separates the fragments by their M by Z ratio. So that is what you can separate. If there are some interference of 2 or 3 molecules coming together, they can be separated. Now then, liquid chromatography nuclear magnetic resonance, or LC-NMR. In LC-NMR, LC and NMR are combined for analytical use. Now you know the NMR spectroscopy is a powerful technique that exploits the magnetic properties of different molecules. Now the resonance frequency of a molecule varies within the intramolecular magnetic field present around an atom. Now this variation can help in the study of the molecule's electronic structure. So in LC-NMR, the sample containing loops are transferred to the NMR spectrometer after chromatographic separation. So in a sample, if it is a mixture of various components, so you cannot do NMR of that mixture because it will be a very complicated spectra. So first you have to separate those components, and then that can be sent to the NMR. So therefore it is LC-NMR is there. So now NMR is, which is normally NMR technique, you all must be aware that it is used for structure elucidation of various organic compounds. Now separation and isolation of the individual components of a sample mixtures are very normal step before analyzing. So either you do it offline or you can do it by online through the LC-NMR instrument, so that LC will do the work of separation and NMR will provide you the structural elucidation. So now You must be aware about the principle of NMR. So what is that? It's the nuclear magnetic resonance. Is a powerful analytical technique used to determine the structures, dynamics, and chemical environment of molecules. It works by detecting the interaction between atomic nuclei with nuclear spin and an external magnetic field. So now many atomic nuclei such as say proton or carbon-13, they possess a property called spin, behaving like tiny magnets. So nuclei with odd mass or atomic numbers have a non-zero spin. Now when they are placed in an external magnetic field, this spinning nuclei align either parallel, that is low energy state, or anti-parallel, that is the high energy state, to the field, creating distinct energy levels. So they are their spin energy levels. Now, when this electromagnetic radiation or radio frequency of a specific frequency is applied, the nuclei absorb this energy and transition happens from the lower energy state to the higher energy state. So this frequency is known as the Larmor frequency and given by this equation given here. So now after absorbing energy, nuclei relax back to the ground state, emitting electromagnetic radiation. And now this emitted signal is detected and transferred into a spectrum using Fourier transform. So that is how you are getting a NMR spectrum. So this is a typical pictorial depiction. So this is a diagram of like normally your block diagram of LC-NMR. So here HPLC columns are there and then NMR is there. So now precaution, what precaution one should take? The LC-NMR, one of the main concern is how to suppress the NMR signals from the solvent, which would otherwise mask the analyte signal. Because in case of when you are taking your NMR, that time you must be aware that your sample will be solid, which you will be dissolving it in a as required solvent, like sometimes deuterated solvent and all. But in case of when you are coupling LC with NMR, so whatever is the mobile phase, that will be going along with your sample. So this can be achieved using solvents that minimize distribution to the proton. If you are doing the proton NMR, then you have to choose a mobile phase which will give minimum interference, such as acetonitrile in D2O, that is, and also its pH is adjusted with sodium phosphate. Now this causes the problems in MS due to deposition of the phosphate salts in the source. So if MS is hyphenated, then to eliminate the proton NMR signal altogether, deuterated solvents such as D2O, acetonitrile, D3 or methanol D4 are generally used. So if you are doing proton NMR and your sample is active for that, your analyte is active for that, then like normally in case of NMR, you take deuterated solvent. In case of LC-NMR, you need to take the deuterated solvent as the mobile phase, so that to avoid the interference from your mobile phase or from your solvent. So apart from pharmaceutical industries or for drugs and metabolites, LC, NMR, MS has been successfully utilized in several other areas, such as the analysis of natural extracts, like flora and fauna. From their natural extracts are coming there, combinatorial peptide mixtures, food extracts and polymers, etc. So now this is the liquid chromatography hyphenated with Fourier transform, the block diagram. So now sometimes the solvent has been removed from after separation from LC, so that it can be directly introduced into instrument. So this is the block diagram for that. So here you can see from LC it is coming. So now that is the cyclone evaporator is there. So that is where air-cooled condenser, then chilled condenser, and then waste solution. So now the cyclone evaporator means it will be by rotating your sample, it will be evaporated. The solvent will be evaporated. Now, direct deposition, GC, FTIR, and data processing. So also GC can be coupled with FTIR also. You know, FTIR also is an important technique for identification of functional groups. When you are producing a new compound, synthesizing a new compound, that time you can FTIR is used to elucidate their structure also. So that time it can be used. So now the various, it can be used to analysis of environmental pollutants such as polycyclic aromatic hydrocarbons, pesticides and herbicides. So analysis of pharmaceuticals such as steroids and analgesics and their impurities, drug metabolites like polymer additives, dyes, non-ionic surfactants and fullerenes, many things are there. So distinction of isomers can be done because the mass you can couple, so isomers can also be separate, like distinctly known. And separation of secondary structure of proteins such as beta globulin, lysozymes, these are the various applications. So even in speciation, you can use your hyphenated technique. So speciation, as the word is borrowed from biology, is a term describing the existence of various chemical and physical forms of a particular element, while speciation analytics denotes the determination of those forms. Now, the notion of speciation is used in chemistry, like what is speciation is in which form it is present. Like say in one of my class I was talking about the inorganic species, say arsenic 3 and arsenic 5. What is arsenic 3? Means arsenic 3 plus and arsenic 5 plus. So now this type of speciation in your sample, whether 3 plus is present or whether 5 plus is present, means element at various oxidation states or bound with different ligands. With which ligands? Say in case of mercury, if it is present, whether it is a methyl mercury present in a fish sample or what is the form it is present. So sometimes it is very necessary to know the species rather than the total concentration in solution. Because methyl mercury is more toxic than normal mercury. Arsenic 3 is more toxic than arsenic 5. Antimony 5, like chromium 6 is more toxic than chromium 3. So rather than, sometimes it is very necessary to know the species which is present in your sample rather than your total concentration. So in case of spectrophotometric technique, we cannot do that. We always need be knowing the total concentration. Though in case of spectrophotometry, sometimes by doing some molecular spectroscopy that can be done. But a normal atomic absorption or ICP-OES, it will give always the total concentration. Whereas electrochemistry can provide you a very good speciation. And then now your LC, GC also can provide you speciation. Now, arsenic speciation, arsenic occurs in several hundred of minerals, mainly pyrite, lead, in copper ores. So it also appears in nature in a number of organic compounds also, such as arsenate, arsenic acid, H3ASO4, arsenite, like this. So dimethyl arsenic, this structure is given here. Then this is one. Like this type of various forms are present in your environment. So if the samples in which all these species are present, if you are going to do it by say HGAS, like the hydride generation atomic absorption spectrometer, then it will give you the total arsenic. But in case of LC or GCMS, you can get what are the species present, each and every species, because for every species the mass is different. So you can know that. So these are just giving some table where you can see what are the analytes and what is the column used, what is the mobile fuel, and which is the method of separation is used. So this I have taken from a normal journal paper. Here you can see the reference is given here. This is just to give an idea how these hyphenated techniques are used for arsenic speciation. If these various species are there with these analytical columns, with this mobile phase, you can very well address this speciation of arsenic. Similarly, antimony also, antimony 3 and antimony 5. So the most important problem with respect to speciation analytics of antimony and its compound encompasses the following, like standards of antimony compounds are unavailable and unstable. Antimony 3 and antimony 5 standards are unstable. They can interconvertible to each other. There are no certified reference materials for antimony compounds, and suitable standards are very difficult to obtain in chemical reactions. So very few inorganic gases like methyl 3 antimony compounds are commercially available. Only trimethylated pentavalent antimony species are produced with suitable purity and sufficient amount. So now there appear problem with low and ultra low analyte content in the sample, especially those with complex matrices. So there exist problems related to unsuitable peak resolution and detection. Peak tailing, especially in the case of antimony 3 peaks, appears while using liquid chromatography. So now antimony 3 forms divalent and sometimes trivalent ions in water solution, and that strongly reacts with the resin, because if you are using some resin, some solid phase extraction you are doing to remove antimony 3 5 from your water, groundwater, so it can react with the resin and you can getting these components in your solution. So how to know that whether your resin is getting degraded or this type of species is coming into your solution? So all these things can be done by your antimony speciation. So again, there is a list which also has been taken from a reference, how antimony various species can be separated. So these are the analytical column, these are the mobile phase, these are the methods, various methods of separation. So you can go through the reference if you are having any such issues. So this is what all about this. So now you can I am yet to get any mail or anything from you. Now I am going to prepare the question paper. I have been told to prepare your assignment and that has to be sent to you all. So in between there are few days of times. If anybody is having any question or anything, any clarification you require, you can send a mail to me and then that can be addressed. Otherwise, whatever question will be said, they all will be from this presentation slides only. Thank you. अभी आप साइड देना, अटेंडेंस देना है ना आपको साइड में. कुछ नहीं